The pitch usually sounds perfect. You have a heavy workload, so you split it across 3 language models: a researcher to gather sources, an analyst to synthesize them, and a writer to produce the final draft. But 6 weeks into production, the team is stuck in a war room. The researcher is returning valid sources, but the analyst rejects half of them as off-topic. Meanwhile, the writer is drafting reports with fabricated citations because it's reading the analyst's summary instead of the original text. If you check the logs, every single agent passes its individual evaluation, yet the system as a whole is entirely broken. Adding a second agent feels like it should linearly double a system's output. The math is less generous. With 2 agents, you have 1 point of contact. With 4, you have 6. With 8, you have 28. Every new connection in the graph is another opportunity for context to be lost or corrupted, squaring the surface area of failure. The protocol connecting these agents is the system. Its design determines whether the workload succeeds or collapses. Examining the structural logic reveals the first major suspect, the routing topology, known as the supervisor pattern. It mirrors a standard corporate org chart. A central manager delegates tasks to specialized workers. But this assumes the AI workers possessed human common sense, that they will naturally fill in the unstated context a human employee would understand. Because they don't, the central supervisor node is forced to explicitly process every piece of routing logic, policy rule, and success criteria for the entire network. As the worker pool grows, that central context window swells, decisions become slower, and token costs skyrocket. Imposing human management hierarchies onto language models creates a fragile, centralized, single point of failure. Beyond the structure, the bloodstream of the system is the next major vulnerability. Most teams rely on plain text prose for agent handoffs. This enables the cascading hallucination attack. An agent invents a falsehood during a routine task. Because the handoff is plain text, downstream agents accept that fabrication as absolute truth, laundering the lie into the final output. Then there is the coordination loop. Agents end up endlessly critiquing each other's work, firing the prompt back and forth without ever making forward progress. Without proper circuit breakers on the conversation graph, these loops become a financial drain. In one case, an unmonitored network ran for 11 days, racking up a $47,000 compute bill. This mirrors the transition engineers made when moving from monolithic software applications to microservices. Multi-agent AI is a distributed systems problem. When multiple models converse, they introduce operational risks that do not exist in single-agent systems. The fix is to stop treating the individual agent as the unit of design and start engineering the conversation itself. To secure these handoffs, the system harness needs to enforce a message contract. Every inter-agent message must follow a strict, typed schema. First, a cryptographic sender ID prevents identity spoofing. Second, a strict scope boundary physically limits what the receiving agent can execute. Finally, hard evidence forces agents to prove claims with source documents, neutralizing cascading hallucinations. Enforcing these contracts replaces the chaotic manual debugging of the war room with a secure, automated audit trail. This protocol mode allows agents to cross organizational boundaries. It turns the conversation graph into a defensible asset that regulators and boards can actually trust.